Hello. In this video, we will investigate whether a droplet wetting a cylinder prefers a shape with the topology of a torus wetting the cylinder, or with the topology of a sessile droplet. So, let's launch Interface Equilibrator. And then I load this configuration file, where I save the configuration that I prepared before. In this configuration, I have a solid surface mesh with a cylindrical shape and a fluid interface mesh with a toroidal topology. The diameter of the solid cylinder is 0.5 millimeter. The fluid interface mesh has two boundaries, both constrained on the solid cylinder. The fluid inside this fluid interface mesh has an almost zero volume, and it is the fluid below the fluid interface mesh, as shown by the normal arrows. So, this fluid interface mesh defines a droplet with an almost zero volume, and the topology of a torus wetting the cylinder. The two boundaries of this toroidal fluid interface mesh are constrained on the cylindrical solid surface. The selected Young's contact angle is 30 degrees. In the last part of this video, I will show you how I created this fluid interface mesh using Interface Equilibrator's built-in meshes. In the experimental parameters, I activated the gravitational force, which is antiparallel to the Z versa, and I selected realistic values for a water-air interface, where water is the fluid below the fluid interface. So, we are simulating a water droplet wetting in horizontal solid cylinder with Young's contact angle 30 degree. In the equilibration settings, I select to grow the volume of the water droplet by 1 cubic millimeter. So, since the water droplet has an initial zero volume, we will simulate a water droplet with volume equal to 1 cubic millimeter. Let's launch the equilibration. As you can see, the water droplet has grown to a volume of 1 cubic millimeter, and its equilibrium shape, which has a toroidal topology, is stable. We can now launch a new equilibration to further refine the mesh. So, I select a higher degree of refinement for the mesh, allowing to refine the mesh up to 2,000 vertexes, and I deactivate the option to grow the droplet volume. Let's launch the equilibration. And so we have obtained the equilibrium shape of the same droplet, but with a more refined mesh. Now let's try to repeat this calculation, but using a different Young's contact angle for the water droplet on the cylinder. So, I first reload the same initial configuration that I used before. Then, I edit the value of the Young's contact angle on the solid cylinder. Before it was 30 degrees. I now set it to 60 degrees, so the water droplet will form a slightly larger contact angle on the cylinder surface. The experimental settings are the same as before, and I select again to grow the droplet's volume by 1 cubic millimeter, so that we will simulate a water droplet with the same volume as before. I now launch the equilibration. This time, due to the larger contact angle, the droplet's toroidal topology is no longer stable, and the droplet tries to form a sessile droplet topology. If we hide the solid cylinder, we see this piece of collapsed fluid interface mesh. This is because the mesh cannot change its topology during the equilibration. However, the droplet is clearly not stable in the toroidal topology, and it is trying to evolve towards a sessile droplet topology. To verify this, let's simulate the same droplet, but using a sessile droplet topology for the fluid interface mesh. So, I loaded this other initial configuration that I prepared before. In this configuration, we have the same solid cylinder and a fluid interface mesh with a sessile droplet topology. The experimental parameters are the same as before, so we are simulating a water droplet in air and wetting the solid cylinder. I select to grow the volume of the water droplet by 1 cubic millimeter. So, we will obtain a droplet with the same volume considered before. Young's contact angle is 60 degrees. That is, the value that before gave us an unstable toroidal droplet. By launching the equilibration, we see that indeed, the droplet equilibrium shape with the topology of a sessile droplet is stable. Let's now launch another equilibration, just to further refine the droplets mesh, like we did before. And so we have obtained the droplets equilibrium shape with a more refined mesh. Now I want to see if the sessile droplet topology is stable. Also for the contact angle that before gave us a stable toroidal droplet. So, I reloaded the initial configuration with the fluid interface mesh having a sessile droplet topology. I select again to grow the water droplet's volume by 1 cubic millimeter. But, this time, I set a Young's contact angle of 30 degrees, instead than 60 degrees, inside the droplet. For this contact angle, we found before that the water droplet with a toroidal topology has a stable shape. However, now we see that also the sessile droplet topology forms a stable shape. So, we can conclude that, for this contact angle, both the toroidal topology and the sessile droplet topology are stable for this water droplet. Like we did before, let's launch another equilibration, just to further refine the droplets mesh. In conclusion, we have found that, at the equilibrium, for a contact angle of 30 degrees, the water droplet can wet the cylinder with either the sessile droplet topology or the toroidal topology. That is, these two equilibrium shapes of the droplet are metastable. Instead, for a contact angle of 60 degrees, the water droplet can wet the cylinder only in the sessile droplet topology. These results can be summed up in this phase diagram, where we show, for the droplet's volume considered, which are the stable shapes of the droplet for the different Young's contact angles that we tried. In the last part of this video, I will show you how I created the two initial configurations that we used for the previous simulations. Firstly, I loaded the mesh for the solid cylinder, using Interface Equilibrator's built-in meshes, and selecting the cylindrical mesh with a diameter of 0.5 millimeter and length 2 millimeters. Then, I rotated this cylinder in the horizontal direction. Notice that the cylinder's orientation is relevant, because in the previous simulations, we included the gravitational force, which is antiparallel to the Z versa. Then, to create the initial fluid interface mesh for the droplet with the toroidal topology, I loaded the circular fluid interface mesh. Along its azimuthal direction, I selected 10 vertexes, and along its radial direction, I selected 4. As radius for the mesh, I select 1 millimeter. After loading this mesh, I rotate it so that it is vertically oriented with respect to the cylinder. To create the droplet's toroidal topology, I remove the inner facets of the fluid interface mesh. We have now created the correct topology for a toroidal droplet wetting the solid cylinder. I will now translate the outer vertexes of this fluid interface mesh slightly in the y direction. I do this so that, when we will select the cylinder as constraint for the two boundaries of this fluid interface mesh, the obtained toroidal droplet will not have an exactly zero volume, but slightly larger than zero, so that we can easily discern which is the fluid below the fluid interface. As indicated by the mesh's normal arrows, the fluid below the fluid interface is that to the right. So, when selecting the cylinder as constraint for the mesh two boundaries, the fluid below the interface will be the fluid inside the toroidal droplet. We have now selected the cylinder as constraint for the fluid interface's outer boundary, so the boundary's vertexes have been moved onto the cylinder surface. We now select the cylinder also as constraint for the fluid interface's inner boundary. And this is the initial fluid interface mesh that we used in the simulations before, for simulating the toroidal droplet. The Young's contact angle of the droplet on the cylinder can easily be edited by right-clicking the solid mesh node. We now remove this fluid interface mesh to create the initial configuration for the simulations with the Sessile droplet topology. We load the fluid interface mesh with the Sessile droplet topology, selecting a very small volume compared to the cylinder. The fluid interface mesh is loaded. We cannot see it because it is positioned inside the cylinder. If we make the solid cylinder semi-transparent, we can now see the loaded fluid interface mesh. I now rotate the fluid interface mesh so that the droplet's boundary is towards up and the droplet's body towards down. Then, I translate the droplet mesh in the Z direction to position it below the cylinder. Finally, I select the cylinder as constraint for the fluid interface mesh boundary. And this is the initial configuration that we use for the simulations with the Sessile droplet topology. Thank you for having followed this video. For more information and for other tutorial videos about Interface Equilibrator, please visit our website.